Sådan. Should we get started, Christian?
Let's do that, yes.
Okay. Hi all, and welcome to our Easter webinar. The topic today is extremely interesting. I've personally been looking forward to this presentation today by Christian. It's going to be very, very interesting, and it addresses one of the big, of course, questions in geotechnical engineering associated with friction angles and more specifically the question of how to choose a correct friction angle in 3D. And Christian will try to answer this question today in this webinar, and also introduce our new soil model for the same thing. We've actually this is the world premiere of our new sand model called FASD sand that Christian will talk about, and so we'll be covering everything from Eurocode to some historical stuff, FE, 2D, 3D, experimental data research, and it's going to be really good. So as always, at the bottom of the screen, there's a Q&A field. Feel free to use that. And after this presentation, 45 minutes, I think, Christian will answer the questions, and we'll be recording this as always and send it around to you when we're done. So let's just get to it. Christian, please go ahead.
Yeah, thanks, John. I think actually the good news is that it'll be a little less than 45 minutes,
Okay.
probably more,
Okay.
half an hour or so. Yes, so this webinar is a little bit different from the previous ones that we ran last week and that we've also run previously, because it's not so much on the use of Optum G3 in terms of setting up models and applying boundary conditions and running analysis and so on, as it is about answering this question here that Jan introduced already, how to choose the friction angle for 3D calculations. And it's maybe a bit of a cryptic sort of question, because of course choosing the friction angle for any calculation or settling on the friction angle for any calculation is a bit of an issue. We know that the friction angle is not constant. It depends on the stress level, for example, and it also depends on the stress state. Say, for example, triaxial compression and biaxial compression, you typically measure two different friction angles. And the question is then, which of these should you use in your 3D calculation? In 2D, of course, it's obvious. You should use the plane strain friction angle, if you like. In 3D, it's sort of less than obvious. So this is a question that we have got quite a few times since G3 was released. How do we pick the appropriate friction angle for 3D analysis? These types of analysis here. Just the footings as well. Monopiles is something that we've done quite a bit of work on recently. So 3D analysis, what that can't really be approximated very well in terms of 2D slopes as well. You could probably get away with that as a 2D approximation, but if you want to run it as a 3D problem, you run into the question of what the appropriate friction angle should be.
Christian, just are you sharing your screen now?
I thought I was. Maybe I'm not. I'm probably. Let me see. Yeah, I should share my screen. So, but there wasn't really very many slides to do with initial words there. What I wanted to just sort of show was some typical 3D problems where you are faced with this question of what friction angle you should pick, the one sort of representative of biaxial, say plane strain, or some other friction angle representative of other stress states. And yeah, I got to the monopiles and then slopes as well, which is usually done in 2D, but can be done in 3D, of course, as well. And then you are faced with the same problem of how to pick the friction angle. And also for much simpler problems, this issue comes in. And I wanted to just go through a very simple problem, a circular foundation on sand. So it's an N-gamma type problem. You have a foundation 2 meters wide, circular, and I've written sand here, friction angle of 30 degrees, unit weight of 18 meter cubed. And we want to determine the bearing capacity. And in order to do that, we could pick up Eurocode 7, which says that the bearing pressure is this equation here, 1/2 B gamma N gamma times S gamma, the shape factor, N gamma Eurocode 7 for phi equal to 30 gives us this 20.1, and S gamma is 0.7. You plug that in and you get a bearing pressure of 253 kPa. And that's of course fine. You are kind of done if you've done that, but you might then also want to just check your results with, say, a finite element analysis, for example, with Optum G2, which can do these analyses very accurately, of course, upper and lower bounds. And if you do that, you've determined the bearing pressure, of course, but you can then convert that into, you start with a strip and then first see what is your equivalent N gamma. And that equivalent in gamma is quite different from the one you have in Eurocode. It's quite a bit lower. And then you could look at a circular foundation, compare circular to strip, and then kind of derive an equivalent S gamma, which would then be 1.05 instead of the 0.7 of Eurocode. So the equivalent bearing pressure is this one here, the 280. And if you compare it with the Eurocode result, it's actually not that far from it. It's quite similar. But it is sort of a question of the Eurocode making two mistakes that sort of pull in opposite directions. So two wrongs make a right in this case, which is of course not something you necessarily want to rely on. N gamma is overestimated, S gamma is underestimated. If you take these FE results as sort of the exact values, which they are subject to the assumptions we've made. But then there are people who say that actually, when it comes to the bearing capacity equation, we have made a mistake already. So, because they say that N gamma should be calculated on the basis of the plane strain friction angle. So I just mentioned a generic friction angle of 30 degrees. I didn't say whether that's plane strain or triaxial or whatever. So we should sort of be aware of what angle we're using, and we should use, when calculating N gamma, the plane strain angle. The idea, of course, being that the bearing capacity, like pretty much everything else in geotechnics, was developed with reference to plane strain. So it makes sense to use the plane strain angle. And the S gamma, the reason that it's lower than, let's say, it should be, is because, that's what these people say, it takes two things into account, both the shape of the foundation and also the fact that underneath the circular foundation, we are not at a state of plane strain. So we calculate N gamma on the basis of the plane strain angle, and then we correct for 3D effects, both in terms of shape and in terms of the fact that we are not at plane strain conditions underneath a foundation, and the angle, the friction angle, the effective friction angle would in that way be different. So we should be more careful with what angle we actually use. So let's say that the 30 degrees was the triaxial angle. And then what is the plane strain angle? Well, Jan and I had drilled into our heads as students, I was going to say a long time ago, but let's say some time ago, that the way you get the plane strain angle is you multiply the triaxial angle by 1.1. You then get 33 degrees, and that's the angle you should be using when calculating in gamma. So that gives a somewhat different bearing pressure, 411 now, which is quite a bit above what we had before. And then the question is, what about FE then? We used 30 degrees. That's the result for 30 degrees up here, but should we use 33? Which of these two angles should we really be using? The triaxial angle is probably, it's too conservative probably. We're not at a triaxial stress states everywhere underneath the foundation, underneath the circular foundation. We are not really at plane strain either. So the question is what to use. If you use the plane angle for the 33, well, then you get this number here, 501. So we have four results that are kind of not too unreasonable, and they differ by a factor of 2. So picking the right angle and doing things in the right way seems to be not completely insignificant. And that's what this new FASD model, friction angle stress dependency SAND model, addresses. But before I'll introduce that, I just wanted to go back to, we would say, basics and just say a few words about friction. So again, you can sort of start with 2D, the simplest possible problem in the book, a rigid block on a rigid frictional surface that you drag to failure. We have some shear stresses, we have some normal stresses, and this block fails once a critical ratio between the shear and the normal stresses is attained. This ratio is the friction angle. We can plot this sort of failure criterion, and then we can instead characterize this failure envelope by the inclination to the horizontal, and that gives us the famous Coulomb criterion. Shear stress is equal to the normal stress times tan phi at failure. So it again, like everything else pretty much in geotechnics, starts in 2D, and then you somehow generalize in a straightforward, more or less way to 3D. So you can generalize the Coulomb criterion to 3D by saying that, well, failure occurs once this Coulomb criterion is satisfied on some section, on some plane within the material. So again, it is essentially sort of a 2D criterion that you then can generalize to 3D, and you can write it in terms of principal stresses as well. That's not exactly a trivial exercise, but it can be done. And you then get this Coulomb cone. There's some cohesion added here as well. You can, of course, do that. But it's this cone with a hexagonal cross-section, and these red points are the triaxial compression corners and triaxial extension in green. And then, of course, the question is, how well does this one parameter model match the experimental data? So if you do a triaxial compression test, you can match the Coulomb criterion to that the data point, well, then you're done. You've determined your friction angle in that way. And the question is then, how do things look when you move towards triaxial extension? Is it a straight line? What happens in between here? And people have tried to answer that experimentally. Lard in 1984, where this data is from, and you can see these are the squares are experimental data, and then the Coulomb criterion matched in triaxial compression. That's good, but it doesn't really match the data anywhere else. So the friction angle, doing it this way, is kind of quite severely underestimated. So it's the same for clays, by the way. So for clays, we tend to use the Tresca criterion. You can see that's not really a very good match. Maybe we should have another webinar about that. But if we look at the friction angle, well, it is, and you can look at it in this plot here as well, versus the B value. The B value is this ratio between the principal stresses. It's sort of kind of similar to the load angle. 0 is triaxial compression, 1 is extension, and somewhere in between, Lada, and this is from Lada as well, have found experimentally that plane strain is somewhere in around be equal to 0.25. So this is compression, extension, and then plane strain would be somewhere more towards the triaxial compression corner. And so this is a loose, medium, and dense sand. And if we had just, to indicate if we had matched the Coulomb criterion in triaxial compression, well, we would have just a straight line here. The plane strain friction angle would be quite severely underestimated, about 40 degrees versus 35, which for bearing capacity problems could be, I think, at least a factor of 2, and if not a factor of 3 in terms of bearing capacity. And just to show you that this is kind of well known, that the triaxial compression state is sort of the odd one out. The friction angle is really quite significantly lower in triaxial compression than for other stress states. You would say, well, Coulomb is just one failure criterion. Couldn't we come up with something else? And people have, of course, done that over the years as well. Lade has, I think, at least 2 criteria, and one of them is shown here. So I guess what he's done is match the data in extension and compression. And then, unfortunately, everywhere in between, well, the fit is not exactly fantastic. It's kind of pretty terrible, actually, and it's unconservative as well. So what we sort of started thinking about is looking at these data. How would we fit these points, these data points, these 3 different curves? And one simple way would be to say, well, it's just straight horizontal lines like that, at least for B above some value, I don't know, 0.1, 0.15 or so. It's pretty much just straight lines. So corresponding to a constant friction angle, basically. And then something happens down here close to the triaxial compression corner. So these fits are, I mean, definitely better than the ones shown here. But of course, there is that issue with the triaxial compression corner. So basically what we said is that, well, the more Coulomb criterion is not very good, but it's not completely out either, because it does actually match the data for over a large range of B values here. Here, right? So let's just hold on to that for a little while, and then also maybe revisit another famous criterion, the Drucker-Prager criterion, which is a circle in the deviatory plane. It's a criterion that's not really, it's in all the textbooks, at least on computational geomechanics, but it's not really very widely used at all, because it overestimates the strength pretty significantly if you match it in triaxial compression. It underestimates the strength equally significantly if you do the match in extension, and then you could possibly come up with something in between. I'm not sure that's such a fantastic idea, but the Drucker-Prager criterion is simple, and it is convenient from let's say, a computational point of view. So the idea with the fast sand was to say, well, if we have these data points here, let's just for the time being forget about what happens close to triaxial compression, and then let's do a more Coulomb fit through the remaining points. So we have this thing here, which is a pretty good fit, except here at the triaxial compression corners. But that's then where we can bring in the Drucker circle matched in triaxial compression, so that we basically have a composite criterion that looks like this. So that is the FASD criterion. It's a combined, or we could say composite, more Coulomb Drucker-Prager criterion. The more Coulomb envelope is fitted to the plane strain angle, and the Drucker-Prager criterion to the triaxial angle. So it's a 2-parameter model, 1 parameter for each of these 2, the Drucker and the Coulomb. And so the question is then, we're back to what should be the relation between the plane strain and the triaxial compression angles. So again, this is the Lade data, and I've tried to use this kind of well-known relation. It says that the plane strain angle is 1.12 times the triaxial angle. This is Kulhauer main. It's similar to what we could call the old Danish relation, the one Jan and I learned at university. And there's also a new Danish that's sort of slightly more conservative. It incorporates also the density index, and I believe that's probably inspired by an even older one, which has a different factor here. But even though these four formulas are quite different, I mean, there seems to be quite good agreement that the plane strain angle is probably something like, say, 5 to 15% greater than the triaxial angle. These red lines here is the first one, the 1.12, and you can see it's not too bad. The medium sand here is maybe the one that provides the best fits. Maybe the dense one is a bit too conservative, but not really bad fits at all. And if you look at it in the deviatoric plane, something like this. And I tried, I have to say as well, all the curved Lade Matsuoka Nakai type Coulomb alternatives, and this one is really, I think, the one that fits the data in the best way. So, and it's of course a very simple model. It takes these two angles as the input. So we can then return to the circular foundation, and then now with Optum G3. And what I've done is I have set up the problem, or three different variants of the problem. So 1/4 of the model, here's my circular foundation, modeled by N prisms, and then the soil domain. And so I first solved the problem for a more Coulomb material with a friction angle of 30 degrees. So that's the triaxial angle. Then 33 degrees, the plane angle, and then the FASD model where I have two angles. I have the 30, or actually the way the input works is you input the triaxial angle and then this ratio between the plane and the triaxial angles. And then this one is calculated automatically. We can just try if we put, say, 35 here and then 1.12, well, then this one is not editable. It's just to sort of as a verification that the number is reasonable. Now, and the results, well, then they're not really too surprising. We can look at some shear dissipation, and this is sort of how it looks. This is sort of the typical failure. We had a huge sort of this stress concentrations here around the edges of the foundation. And if we look at the actual results, well, more Coulomb 30, so triaxial angle this much, plane that much, and then the FASD somewhere in between. If you normalize by the FASD results, well, you get that the triaxial result and the plane strain result are about the same distance from the FASD model. So the FASD model is really sort of the ideal compromise between these two. The problem is you don't know which of these two angles is really the better one, and in this case they're equally bad, you could say. The FASD model kind of resolves that issue. The errors here, just to show that there is Chris Martin's ABC where you can, there's Optum G2 as well, where you can get these results pretty much exactly. And just to show you, these are typical errors in the more Coulomb calculations, 10,000 elements and 3 adaptive iterations. Of course, with 20,000, it would be even less, but quite small errors. And then I just want to show a second problem. This is a rectangular foundation now subjected to an inclined load, same material parameters as before. So an inclination of 25 degrees. And the results here in normalized form, so FASD is 1, and then the more Coulomb with the plane angle, 9% above, and then the Coulomb with the triaxial angle, about half the capacity. So in this case, the results are much more reminiscent of a more Coulomb with the plane angle, of course, because this problem here, the failure of this problem here, and I have the results here, is much more akin to, you could say, plane strain conditions. So there's a kind of a sliding. This is a pretty significant inclination for these parameters here. So there's a kind of a tendency to almost sort of a sliding along the surface here. So again, let me show you some shear dissipation, and so it sort of looks like this, right? I play the movie. It kind of looks a bit odd, this movie, but this thing here is actually displacing just in this direction here. And the failure mechanism is kind of a plane strain type mechanism. Not quite plane strain in terms of capacity, 9% from plane strain, but much closer to plane strain than triaxial compression. So it's really problem dependent. If you only have more Coulomb at your disposal, what friction angle you should use. And the FASD model kind of resolves that issue. You pick, input your two angles, and then your results will be consistent with that. The last thing I wanted to just say something about is something that always was a bit of a mystery to me, and that is the shape factor. I call it the shape factor mystery. And well, the mystery, what was always a mystery to me is that in some codes and in some textbooks and so on, you see a shape factor as gamma less than 1, and in other texts you see 1 greater than 1. So the Eurocode 7 says 0.7, the Danish National Annex is even more conservative, 0.6, then there's Brio, 1.25, Meyerhof, a quite well-known equation, which also incorporates the friction angle. For 30 degrees, it would be a shape factor of 0.3. So the mystery is not so much the actual values of these. The mystery is a circular foundation stronger or weaker than a strip foundation? I thought that would be something that would be possible to settle. So, but there's apparently two schools of thought on that question. If you look at experiments that people have done, and these of course should be taken with a grain of salt, these experiments are really kind of difficult to do, and it should really be full-scale tests, ideally speaking. So anyway, experimental data sort of, or experimental findings of S-gamma tend to support an S-gamma slightly below 1. There's a funny detail that Golder, 1941, did some tests and he concluded the shape factor is 1. Sasaki, on the basis of the same experiments, concluded 0.8. So there's also that aspect to it. There's the scatter of the data and so on. But slightly below 1 is what experiments tend to show, I think is fair to say. With the FAST model, we could have a look at how things look. And this is, I've used the square foundation now, and we could look at just the square foundation, but for general rectangular foundations. And we did that. These calculations can be done really in a quite straightforward manner. Of course, the more elements you use, the longer the computational times, but eventually you get there. And if we look at then a circular and a square foundation, so this is how the shape factor looks. I don't really like calling it the shape factor, but let's say the capacity relative to the capacity of a strip versus the triaxial compression angle. So there's a slight difference between circular and square. And well, you see, let's say effective shape factors somewhere around 1, but typical design friction angles, 30, 35 degrees, it's sort of slightly below 1. For higher angles, it's slightly above 1. Well, there is maybe good reason for this disagreement of whether it should be above or below 1. Sometimes it's 1, sometimes it's the other. It really depends on the friction angle. At least that's what the FAST model says. So it's kind of, I think, consistent with these equations and also with the experiments. So they do that experiment, the strip and the circle and the squares do tend to have somewhat less capacity for smaller friction angles than the strip. So I think that's, to me at least, that was sort of the mystery resolved, and that brings me to the end. And I'll be happy to, of course, to take questions. Oh, Jan is somehow muted. Let me just see.
Oh, sorry, I'm here, Christian. Yeah.
Okay. So what type of test do you use to determine the plane strain angle? Yeah, you could say you could use a biaxial test. That biaxial test is not a straightforward test to do. I mean, that's somehow the problem, that the most common and easiest test to do, of course, is the conventional triaxial compression test that gives a lower friction angle than pretty much for all other stress states. These data here of lattice have been obtained with true triaxial testing, which of course is even more complex than even biaxial testing. So it's not exactly a routine thing to do, but the point I was making with these 4 equations here is that there is actually quite a bit of experience and knowledge out there, and some of these equations are in the codes. So in any given situation, what exact number should you pick? I mean, I think there's the old Danish one, the 10% one is probably as good as any. I'm not sure there is this dependency on the relative density. These Lotte data don't really show much of that type of dependency, that this ratio, the plane to triaxial ratio, should depend on the density. So that's sort of what I can say about that. The last graph, yes, those results were obtained with the FASD model. These ones there for the shape factor for circular and square foundations, they were obtained with the FASD model using this factor of 1.12, which is what I used throughout here. So the plane angle being 1.12 greater than the triaxial angle, and you would then get these results here. Of course, in the strip calculation, you're a plane strain, so in that case you use the plane angle in a regular, more Coulomb type analysis. Then there's a question about stress dependency, and that's of course very true, as I said to start with, that the friction angle is one of the most non-constants, maybe constants that we use. It depends on the stress state, or the load angle, as it's also sometimes with this B ratio, and it also very much depends, of course, on the stress level. Now that's included in one of our other models, the GSK model. It's not included yet in the FAST model, but it's a question of getting it in there. We have it actually kind of in it's not available yet, but it's going to be out there very soon. So then there's another, you could say, nonlinearity, or another source of non-constancy, namely the stress level, so that the friction angle is, of course, increases quite significantly with decreasing stress level. So that's an effect that that under the right circumstances is important as well. Have we tried the FAST model for back analysis of full-scale bearing capacity failures? We haven't done that, no, and it would be something that would be interesting to do. Now, full-scale tests, the results of full-scale tests are not necessarily that easy to interpret, but that could easily be done, and I'm pretty confident that we would match those as well as with any other model. The point with this model, though, is you could say, I don't want to say the point is not accuracy, because of course it's accuracy as compared to experimental data or full-scale data, the real world. But the point was more that when doing 3D analysis, and more Coulomb is the only model at your disposal, you have this dilemma of what angle to put in. The triaxial compression angle, which is usually the one that is available, or the plane strain angle. So you know that probably the triaxial compression angle is somewhat conservative, but can you really go for a plane strain angle with the more Coulomb criterion? Well, not really. It's somewhere in between. Where in between, you don't know. And the FASD model then allows you to basically input both angles and have a result that is sort of consistent with that, and also consistent, I think, definitely with, as I showed here, with experiments, lab scale experiments. Cohesion is not included. Cohesion could be included, but this is a sand model. Cohesion would be quite trivial to include, and maybe we'll do it at some stage. There's a comment that I guess it'll take some time for the model to come to optimize. Thinking of doing it. We have actually done it. It's available now for download in the latest version of Optum G3, the FAST model. So you can check it out for yourselves, and now you have some results to to benchmark against. So unless I have made any mistakes, this is what you should get.
Yeah, regarding the release, it's not put up yet, Christian. It will be put up later, today or tomorrow. So when I send out the mail with the link to the video, I'll probably also include the just info about when the installer will be up. But yeah, it's going to be up today or tomorrow.
Okay. Then there's an interesting comment that Liamin et al. 2007 in a geotechnique paper using discrete element modeling also provide an expression for N-gamma that is some expression there given. And that gives values of greater than 1.2 for phi equal to phi greater than 45 degrees. Have I seen that paper? Yes, I have seen that paper. It's not very clear in my mind, but I have a good idea of what you're talking about. I don't think it was discrete element modeling. I think it was limit analysis that was used to basically obtain shape factors for various rectangular foundations in that paper. The problem with that, of course, is that the more Coulomb criterion was used. So the more Coulomb criterion has a constant friction angle. So if you're of the opinion that the shape factors that we operate with in the analytical bearing capacity equations cover two effects, the shape itself and also the fact that the friction angle varies between plane strain and 3D conditions, then these shape factors of Liamin, I'm afraid, don't make that much sense, because the friction angle was constant. It was Coulomb throughout. So they of course make sense on the basis of that assumption, but that assumption is not really a very good assumption. If that makes sense. Drained analysis of clays, yes, I think it's the same kind of thing. I think you have exactly the same effect for the drained friction angle of clays. There's a lot less data out there, but I have seen data that I've seen tend to suggest that there is this effect as well. I showed you some before, but there are others as well. So I would say yes, there is probably the same effect for clays as well. Um, friction angles change in real situations. Friction angle change depending on stress state. That is exactly, I mean, depends exactly what you mean by stress state. So if we say the load angle where you are, that's what this model takes into account. Then there's the question of the stress level dependency. That is not included in this model. That is coming soon. But what is online now is the load angle effect, the plane versus triaxial effect. Have we considered applying it to thermal expansion scenarios for bridge designs? No, but that would be an interesting application. If that's something you would be interested in discussing, we would be interested in discussing it with you. Yeah, I mean that's the thing with lab tests, and so the conventional lab tests, direct shear and triaxial compression, maybe triaxial extension, and yeah, well, so the direct shear, of course, it was what would be more representative of plane strain conditions. The direct shear test has some other inherent problems, so it's sort of difficult to say which test to rely on more. I think the triaxial compression test is probably the most reliable one, but it's also the one that gives the smallest friction angle that you would then have to somehow estimate your plane strain angle on, for example, some of these four formulas that I showed you before.
Yeah. So say, Christian, you as an engineer, you got a triaxial friction angle. How would you convert that? Which factor would you use?
I would, well, it depends. I mean, I would go into my local code and see, does it say anything about it? If I'm in Denmark, it does say something about it. If not, then
Yeah.
I would say probably 1.1 is as good as anything.
Yeah.
I have looked through, I only showed you the lattice data here, but I've looked through quite a lot of other data, and it seems to be around, I think even 1.1 is somewhat conservative. I think it's rather 1.12 is better. To say 1.14, 15, something like that, is what I can see. Seems to be pretty consistent. Okay, then there's a kind of a comment that someone has carried out a lot of tests and you get the same friction angles, but I mean, that's, again, you're welcome to discuss, to contact us for a further discussion, but this type of trend with the triaxial compression angle being smaller and then the friction angle gradually increasing, or abruptly increasing, you could even say, is a very consistent trend that you see in lots of other experiments. I showed you this sort of overview here before. I don't know, 4 or 5 different groups have found exactly the same. So I think this is probably the way it is, unless people have consistently been making the same mistake for a very long time. I think this is kind of the trend. Yeah, so
should we call it a day?
I think so, yes.
Fantastic. Thanks for the presentation, Christian. Very, very interesting. And And of course, I'll send around the mail, and we'll get the new version up as fast as possible with this new great SAN model, and you can try it out yourself and get back to us any time if you have questions or comments or anything. And yeah, have a great Easter, by the way, and hope to see you back next week.
Yeah, have a good one.
Yeah, take care. Bye-bye.
Bye.